Okay, so the one new thing we need to do is the force between two current carrying wires. We've already done the force on a current carrying wire in a magnetic field. We've done the force on a charged particle in a magnetic field. And the one we haven't done is a force between two current carrying wires. So here are my two current carrying wires. We can call this one number 1 and this one number 2. And we can say that there's some distance r apart. Okay? And if their length, let's call they're the same length, and let's say that their length is L. Okay? So what we already know is that any current carrying wire, I'm going to make this guy's current going up. So let's say it's going up like this, and we'll make it electron current. So we know this electron current carrying wire has a magnetic field around it. And we could use our first hand rule to find that. That magnetic field would be over here where this second wire is sitting. So this second wire is in the magnetic field of the first one. And the first wire is in the magnetic field of the second one. And I'm going to also make its current going up and its electron. Okay? So we could figure out the strength of the magnetic field of the first wire. So the magnetic field of number 1 would be that very first equation that we learned. B is equal to mu O I1, because it's wire 1, over 2 pi r. Okay? Now, let's assume, I just said they're a distance r apart, so that means I'm assuming the second wire is placed at this point r. And so where number 2 is. So this second wire is going to experience a force because of this field. And so the force on the second wire, F2, would be equal to just B from the first wire, call this B1, I from the second wire, L, the length that's in the field. Okay? So if we take this B and we substitute it in here, we can get an expression for the force of this on the second wire from the first one. So we can call it 2-1 if you want. So it would be mu O I1 and then I2L from here. And it's all going to be over 2 pi r. Okay? Now, we could do exactly the same thing, find the force on the first one, and if you want me to do that, I could. So the first one's on the field, in the field of the second, and the field of the second at that point would be mu OI2 over 2 pi r. And so then to get the force on the first one from the second, it would be of the second times I of the first L, and then substituting this in, it would be mu O, again, this time it would be I2, I1, L over 2 pi r. But I'm hoping that you notice these are exactly the same equation, just the i's are in a different spot, which should make sense. That's Newton's third law. If one puts a force on the other has to put the equal and opposite back on it. So we just say F is equal to mu O I1, I2, L over 2 pi r. Okay? And it'll be the force on each. Okay, so that's the force. Now, one of the things that you should do, and I'll check with you tomorrow to see if you did, prove the units. I is the current in one wire, I2 is the current in the other, L is the distance between them, L is the length of the wire, and R is the distance between them. Prove that when you put all that together, you get back Newtons, okay? And I'll check and see how you did tomorrow. But the other piece is they're putting a force on it, and force means that it has a direction. And technically here, right, there's a sine theta here. So there would be a sine theta here. But because the wires are parallel, this will always be 90 degrees. Because if the wire's parallel, then each wire's field will be perpendicular to the other wire's current. So we usually just drop the sine theta because it will always be 90 degrees. but it does have the force on it does have a direction. Okay, and it's really a combination of two hand rules to get the direction. First, you need to get the direction of the magnetic field from the first wire if we want to find the direction of the force on the second. Okay, so you use the direction, find the direction of the magnetic field from the first wire on the second, and then you use that magnetic field and find the direction of the force. So to find the direction of the magnetic field, first wire on the second, you would take your hands. I should have used right hand current. You take your fingers, point your thumb in the direction of the current, and curl your fingers around the wire in the direction of the magnetic field. And so for wire 1, there's my thumb going up, and my fingers are curling, and over where wire 2 is, they're coming out of the page. So over here, the field from wire 1 would be dots coming out of the page. Okay? Once you have that, now you do the second hand rule to find force, because you have direction of current, direction of field, and this is the palm rule, right? Point your fingers in the direction of the current flow, point your thumb in the direction of the field, so it's going to be coming up out of the page towards you, and the force is going to come out of the palm of your hand and act this way on wire 2, which means wire number 1 is attracting it. You could do exactly the same thing and find the direction of the force on wire 1 from wire 2. So again, first step, thumb rule, point your finger in the direction of current number 2, your fingers curl in the direction of the magnetic field, and so over here where wire 1 is, my fingers are going into the page, so these would be X's. So these X's are from the field from wire number 2. So where wire number 1 is, the field is going into the page, the current is going towards the top of the page, and so the force coming out of the palm of your hand should be this way. So what it's saying is wire 2 is attracting wire 1, putting on a force on it to pull it towards it, and wire 1 is putting a force on wire 2, pulling it towards it. So they are attracting. Okay? Don't worry, we'll do another one together tomorrow in class to get it all straight. So now for homework for today, I would like you to work on this sheet that I will post, and I'd like you to do numbers 1 to 4, numbers 8 and 9, and on the back side, numbers 15 and 16, because they're the two with this new equation. Okay? It leaves us one last new thing to do, and I still have a minute and a half, so maybe I'll just talk about it for a second. The one last new thing is just theory, and it's on something called a galvanometer. Okay? And a galvanometer is a device that's used to measure really small small currents. And if you were to take, we talked about ammeters and voltmeters before. If you were to take an ammeter apart and a voltmeter apart, you would discover that there is a galvanometer inside of each of them. It's the galvanometer that's being used to make the ammeter and the voltmeter. Okay? And the way it works, so when we say really small currents, we're talking like 50 microamps is all that it can hold. And so inside the ammeter and the voltmeter, we put a resistor, either in series or parallel with this galvanometer, to allow it to measure the voltage or the current. And that piece I'll leave till tomorrow because it'll probably be easier to see your puzzled faces in person than just to imagine them. Okay, so this is the last piece we have that's new in the unit. So we will be ready for our test. I think we said Thursday. The snow day will not change the date of it, I don't think. Okay, but we'll talk about it tomorrow. All right, thanks. Have a good rest of the snow day.